Hi, and welcome to the Radiation Research Society vodcast. I'm here with Daniel Adjei, and you are originally from Ghana, but you are now a PhD student at the Military University of Poland.
University of Science.
The Military University of Technology in Poland. Tell me a little bit about how you ended up there.
Well, good. I have worked with the Ghana Atomic Energy Commission for past years, and then I have been a PhD student from King's College London, and then transferred to the Military University of Technology, because the program I am in is a European Union sponsored program from, we get funding for PhD students, so it's a joint doctorate degree. Okay. And so our consortium is a ecstatic consortium which funds all these PhD programs. And it's dedicated for EUV and X-ray science and technology. So we are basically into EUV and X-ray science.
And this is the Erasmus program?
This is the Erasmus program, yes.
Okay. That's great. I know that's a big,
very big,
very popular in Europe for lots of different countries.
Yeah. And the consortium is doing very great.
That's wonderful. So now diving into your work. So this is your PhD thesis project. Yeah. And I have a title here: Design, Characterization, and Application of a Desktop Laser Plasma X-ray Source for Radiobiology Studies.
Great.
So what I want to know is, so this is, I'm just picturing like this little device sitting on my desk that I can use to irradiate mice or cells, or explain this to me.
That is great. That is exactly the model that we have built.
Really?
And for laser interacting with a target, usually we have very big facilities to do that. But the aim of this project was to have a tabletop device, because we feel that radiobiologists are afraid of big machines. So getting a smaller device for such experiments will be fantastic. And this is a very simple, which can fit on an optical table of about 1 meter square.
Wow.
Yeah, so you have the laser system on one side, and then the irradiation chamber on the other side, which will fit on the table. That's why it's called a desktop. And we are generating X-rays in a specific wavelength. For the sake of radiobiologists, the energy is between 280 eV to 540 eV, so very low energy. Okay. The interest of this energy is it's highly absorbed by the elemental components of biological systems, like carbon, oxygen, and nitrogen. And that is the purpose of this device. And it's pretty working well. I have shown typical examples or applications to induce strand breaks in plasmid DNA. So it's working, it's available, and it's dedicated for any radiobiology experiments. Okay. So whoever is interested, it's available.
So it's available. So does your lab produce this? Or are you working with a company that's producing this?
Well, for now, we are producing it.
Okay.
We are still asking for companies who are interested to collaborate with us and maybe commercialize it.
So, I'm not sure about how it works in Europe, but you've patented this.
I'm preparing the patent for that.
Okay.
It's something that a lot of people have recommended that I do it. And so it will be patented very soon.
So you have a lot of interest from other researchers around the world?
Exactly. Now we are collaborating with radiobiologists in Krakow, it's another city in Poland, also with colleagues in Czech Republic, in Prague, to irradiate some lipid membranes. And then, as I told you, we've started with plasmid DNA, where we induced strand breaks using the source. We intend to demonstrate the application with the use of cells itself, and then probably for further radiobiology experiments. But for now, this is how it is. It allows you to irradiate your samples both in the vacuum condition, if you are dealing with dry samples, or outside the vacuum chamber, if you are dealing with wet samples like cells or like lipids. And it gives very high dose. The main features of this source is that it allows you to irradiate samples very fast, in nanoseconds. In a nanosecond, that is one shot, you have huge dose to your sample. Meaning, if you want to do, irradiate samples in a very fast way to analyze, it's available.
So is this only being used in vitro, or could you use it, like, say, in an in vivo situation?
In vivo will be difficult due to the attenuation length of these soft X-rays.
Okay. I'm not too sure about
exactly.
that.
Yeah, I agree. But then we can go into very high energy X-rays if we change the laser system and then using a different target. I'll be glad if I'm allowed to tell you the target. The target is already patented. It's a property of the institute.
Okay.
Yeah, it's not a solid target. This is a gas-powered target.
Okay.
This target is very unique, unlike the solid targets which creates debris. Debris are the particles that are generated in the solid target when the laser interacts with it. Okay. But in this case, this is a gas, and the gas is a double-stream gas per target, the system. What it means is that you have your working gas coming in the middle of the valve, and then there is a second gas, which is a light or low Z gas, which confines this working gas. So you can have a stream of gas, and then the laser interacts, creates a plasma. And you know, the plasma is a plume of ions, electrons, and neutrons. Okay. And they interact and generate the X-rays due to free interaction or bound interaction, a lot of atomic processes going. Right. So the first thing is you have a very narrow bandwidth, somehow monochromatic radiation. The second is that you have a unique kind of X-rays. The third is that you have a target which does not create any debris. The fourth is very fast. So if radiobiologists are able to come out with a very fast technique of analyzing your data, then the device, because it's in nanosecond, because you know, radiation interacts with with any matter, starts with ionization and excitation, which is like in the nanoseconds before pre-chemical, effects goes on down to DNA damage and so on and so forth. So if you want to study the mechanism of radiation effect, then this fast system is very good because you can study the fast radiobiological events or mechanisms. So this is very good for unlike the other sources where you have to do long time irradiation, like minutes, before you take out your sample for analysis.
Okay.
Yeah.
So something, this brings up many questions. Something you mentioned in the very beginning when you were describing this is that the reason that you wanted it small is because maybe radiation biologists and researchers are afraid of the big machines. So let's talk about being afraid. As far as protection goes, how do how safe is this as far as, I know you said there's no debris, so, but what about shielding? Do you have to wear something? Is this just going to be like a PCR machine that's on the bench, or is it going to need a special room? Or
I am a radiation protection expert.
Okay.
So, issues of safety and protection, it's something of much concern to me.
Good.
So this device, I can assure you, all the safety systems are in place.
Oh, great.
The interesting thing is that in the chamber, it's a very thick chamber. Of about 3 centimeters thick of the chamber. So there's no radiation coming out.
Okay.
And then the radiation coming out in terms for the irradiation, it's even very soft energy X-rays, which can easily be attenuated by even air. If we go into the higher energy level, like kilo electron volts and so on, we have the means to keep all the protective measures. So that is not an issue with us, with the source at all.
So this would be like a future.
Yeah, for the future.
When you're upgrading this.
There are
to
many
high.
things we can do.
Okay.
With the source, at the request of anyone who is interested. First of all, I know people are interested in microbeam sources, which I started my work with in King's College London to develop a microbeam source. So it is not a new thing that we cannot do. One of them is, in the future, we want to upgrade the system into a microbeam source and mount on it a confocal microscopy or whatever, so you can do lifetime irradiation and look for the possible endpoints that you're looking for.
Right.
So that is a future plan, but it's not any difficult thing. We only want to demonstrate the application now, and all the other accessories can easily be put in place.
So it sounds like your PhD, it's more of a bioengineering focus, but are you also working on applications with this, like looking at samples and testing a hypothesis?
Yeah, as I told you, I have demonstrated the applications.
Yes.
So I'm more or less.
Talk about that.
Yeah, I'm more or less like involved in
in both sides.
In both sides.
That's great.
Yeah, because I have been trained as a biomedical physicist, so I have much interest in understanding the mechanism of radiation effects. For now, I'm not really looking into very serious endpoints or maybe some mechanisms or something like that. The first is to show the application.
So you're validating.
Validating exactly. So as I said, I started with plasmid DNA. So I have irradiated 2 different DNA, PUC19 and PBR322, because they have different base pairs. So I decided to check, long base pairs and then shorter ones to see how the source will be very effective. And in both cases, it shows. The second point is that I irradiated this plasmid in their solution. It comes with TAE solution. It's irradiated in it. And if we look at when the plasmid was irradiated in the dry condition and in the TAE solution, in the water solution, you see there's a huge difference, which can be associated with the creation of free radicals due to this soft X-rays interacting with the water molecules or the TAE molecules to cause further damage. And this is a very known mechanism. So I just wanted to show that these principles work. And it works for such low energy X-rays as well. So it's another very important area to look more into. Yeah.
So are you planning on moving from plasmids to human cells or mouse cells?
Well, to cells for now. And next week we're going to work with cells.
Okay.
Yeah, we collaborate. The difference we have to know here is that the institute is not a biological institute, it's an optoelectronics.
Right. Okay.
So we are more into the development, but now we want to collaborate, because to work with cells, of course, you need this ethical clearance and all this stuff in the institute. So now we're collaborating with another laboratory who has this opportunity to use the cells. That's why I started with plasmid. That has no problem.
Right.
But with cells now, we have to collaborate with this lab, and they will come with the cells and the samples, and then we will test it.
Is this a lab within Poland, or are you doing any collaborations back with King's College at all?
Not yet, because unfortunately, I might say that I lost my supervisor in King's College.
Okay.
May his soul rest in perfect peace. Alan Bichette, very fantastic man. I love him so much. So for now, I'm not doing any work with them.
Okay.
Yeah, because but then we developed a microbeam. It was almost to completion when he died, unfortunately. But it's moved to another university, Imperial College. I go there most of the times, to collaborate with them as well.
Oh, great.
Yeah. So, but then in the future, I hope to develop my own microbeams as well. And
sounds really exciting.
Yeah.
So, how far away from finishing your PhD are you?
I am not far at all.
Yeah, I was going to say, it sounds like you've done amazing work for just a PhD dissertation.
It's not far at all. The only thing is to submit a thesis now.
Congratulations.
Thank you. So I should have actually finished last month, but I lost my supervisor in King's College, and due to the arrangement with the consortium who is funding ecstatic program, I had to go to my second university, which is Poland. So that resulted in a little bit of delay. And so I have taken 6 months just to finish writing and complete some other administrative processes in the PhD. So yeah, so hopefully latest by February next year, I should finish.
Well, I mean, the work that you're doing is so interesting for just a PhD project. I really look forward to seeing what you do in a postdoc and in the future. And yeah, and who knows, we might see these desktop plasma X-ray sources in labs across the world in the future.
Yes, we will definitely. We're asking for people to come and make use of it. It's available for 24 hours. It's only gas you need as the target, and the rest is there. The laser works 24 hours. The target is there 24 hours. So the source is there 24 hours.
Is this comparatively inexpensive to the larger machines?
Oh, no.
No?
It's not like that. Of course, it cannot perform as the synchrotron facilities.
Right.
But then, looking at what it can do, it's good. It will be difficult to compare prices, but it's nowhere near synchrotron sources. Of course. But then, of course, the application will not be as so nice or state of the art like the synchrotron sources or facilities. But at least within the means, this is available for any kind of studies.
I guess what I'm trying to get at is, funding is difficult to come by.
Sure, that is the main.
In labs across the world. I'm just curious if a lab wanted to do research using this type of X-ray source, would this be a more affordable option? That's not right, more affordable in context, but not as varied in application, but maybe more attainable for labs that don't have as large of a budget.
Yes, I cannot quote the price, but the main cost will be the laser system, which varies according to the energy and then with the pulse rate you want or the repetition rate you want. If you want to use high energy lasers, then of course that will increase the cost. But apart from that, the rest is just assembling of all the different parts, and it can be configured according to what you want. The interesting thing with the current source I have built is that it is emitted in the vertical position, so you can place a sample sitting on the stage like this. I know some sources are emitting horizontally, and you have to, depending on how you deal with gravity with your sample, because I know some are making controversy on the gravity on the sample and so on. But this is, for now, is in the vertical position. It can be made in any kind of position that you want. So that is also another easy thing you can do to manipulate the source. But in terms of cost, as I said, it is reasonable. It is reasonable. Laser sources are not so expensive, so it should be.
Yeah, it sounds interesting. It's so interesting, and I like that it's, able to be designed to what each researcher is interested in. Yeah. All right. Well, thank you so much, Daniel, for coming and talking with us here at the podcast for Radiation Research Society.
But let me make this final comment about my funding agency. That I am so glad, and I want to thank the Ecstatic program, and of course the Erasmus Mundus program, who is funding this project, and then the Ghana Atomic Energy Commission, who has given me the opportunity to study outside. So these are the few things I just want to put on board, and I thank them so much. And you're always invited to Poland to use our source. Thank you so much.
Thank you so much, Daniel. Thank you for talking with us. Have a great day.